right, let's talk about one more of our simplifying principles that make our life easier for rotational motion. We've already talked about several things that we could use in energy methods that pertained to an object rotating around a fixed axis and calculating the change in potential energy and the change in kinetic energy. We did that in the last example problem that we did. Now we're going to consider an object that is rolling without slipping. Usually that's going to be the application we think about. For example, a wheel that maybe is rolling along the ground, and in this case I'm imagining I've painted a stripe on the wheel, and that stripe, is just sort of going around to show the wheel is rotating. And we're going to imagine that the wheel is spinning with angular speed omega while the axle is moving with speed v center of mass. Okay, so here I mean the center of mass of the wheel itself. This may be part of a car, but here we're only considering the center mass of the wheel. So this is how fast the axle is moving, or the center of mass is moving. If an object is rotating about its center of mass with angular speed omega while the center of mass moves with speed v center of mass, how do we write the kinetic energy? Well, we already know if the axis were fixed, we would have 1/2 of the moment of inertia about the center of mass times omega squared. But it's got to be more than that, because if the object were just fixed in space, in other words, if that axle were not moving and the object were spinning with angular speed omega about the axle, that would give a certain kinetic energy. Surely it has more kinetic energy if we take that same object and cause it to, in addition to rotating, also translate through space. There's got to be more kinetic energy than just the term that we have. This is certainly true up here for a fixed axis, but now we're not talking about a fixed axis. There's got to be more kinetic energy than that. And the book derives this relationship, I believe. I'm not going to derive it here, but that additional amount of kinetic energy is nice and simply 1/2 times the mass of the wheel times the speed of the center of mass squared. So in this case, it has to be an object that is rotating around its center of mass. In the usual case, the only case we'll apply this in our class is when a wheel is rolling without slipping as it rolls along, the ground or an inclined plane or something like that. But it's kind of interesting in that it sort of seems to break apart into two pieces: a rotational piece of kinetic energy that has to do with 1/2 I omega squared, and a translational piece of kinetic energy, 1/2 m v center of mass squared. So that's a nice simplifying case to calculate the total kinetic energy of this as it moves along while rotating. Let's do a kind of an example problem, or at least talk about how to approach a problem. Here we're going to imagine we release a ball or a wheel, we won't really specify right now, rolling down an inclined plane, and we release it from rest, maybe up here in the red position, and when it's moved a distance d down the inclined plane, we would like to know, if we release it from rest up here, what is the center of mass final speed down here? How fast is the center of the ball moving? It's, of course, speeding up more and more as it goes down. And I should have said rolling down an inclined plane without slipping. It's possible for a ball to roll down while it's also kind of sliding. But let's imagine the more usual case where the ball rolls, but it's not sliding on the plane. The usual way where, we also don't drive while we're peeling out around, usually in a car. So this is rolling without skidding on the plane at all. We're going to do this by using the energy methods. I'm going to say the net work done by all external forces in between here and here is equal to the change in kinetic energy plus the change in potential energy of a system, and I have to specify what my system is. Here I'm going to take our usual system where we take the object that's moving plus the earth. We take gravity to be an internal force. But there are other forces that are being applied to that moving ball besides gravity. There's the normal force. Of course, there's got to be a normal force being applied to the ball as it moves, because otherwise the ball would just fall right through the plane. And there's also got to be a friction force that is being applied to the ball, because if there were no friction, the ball wouldn't start rolling at all. It would just skid all the way down the plane. So if it's going to roll without sliding, roll without slipping, there's got to be a friction force. And if it's not sliding, that's a static friction force between the wheel and the plane. We'll take those to be external. So let's apply our relationship up here. The net work by external forces is just the normal force plus the friction force. Now, the normal force is not doing any work because the normal force is acting in a direction that is perpendicular to the direction in which this thing, all the movement is happening. So it seems like the normal force can't be doing any work. So we'll leave that off of here. That does zero work. We still have to worry about the friction force work. For kinetic energy, now we have an object rolling without slipping. So we're going to use our more general expression for the kinetic energy, 1/2 I omega squared plus 1/2 mv squared for the center of mass speed. And we'll do that for the final state minus for the initial state. And in the initial state, both omega and v center of mass are 0 because we're imagining we released it from rest up there. So that's why I put the 0 in there. But we got this sort of complicated expression for the final state. And for the change in potential energy, well, delta y center of mass is going to be a negative quantity. And it looks like if it goes a distance d down the plane, then how far it goes down vertically would be d times the sine of theta. Okay, so we'll have minus d sine theta will be delta y. Let's go a step further down. Now, the problem with this expression is that we would like to solve for v center of mass final, right? We want to know what the center of mass speed is here. I don't know what omega final is, but I kind of do in the sense that when something is rolling without slipping, there's a relationship between the v of the axle or v of the center of mass of the ball or v of the center of about which it's rotating as it rolls down. For rolling without slipping, we derived long ago that the center of mass speed or the axle speed is r times omega, where r is the radius of the wheel. So I'm going to replace omega final with v center of mass final divided by r. When I do that down in this relationship here, okay, so I just replace my omega final with v center of mass final divided by r. And I replaced, oh, I see a mistake here, delta y center of mass. There should be a minus sign right here. This should be negative because delta y center of mass is negative. There's a mistake right there. No worries, just imagine a minus sign right there. Now, I've got, if I imagine I know what the angle theta is, someone has given me d, I know what m is, I know what r is, and I can calculate what the moment of inertia about the center of mass is. All of these are details that we can figure out. We want to solve for v center of mass final. That was what we were trying to figure out here. And I can, if I square out this term, I'll have v center of mass final squared divided by r squared. And I have a common factor of v center of mass final squared, which can be factored out of here. I also, oh, I see, yes, no, this is correct. I have factored, there's also a common factor of 1/2 in each of these terms. I factored that on the left-hand side of the big parentheses, and I factored out my v center of mass final squared, which is in both of these terms, on the right-hand side. And everything else that's left, I center of mass over r squared, and m is the only thing that's left in this term here, are shown there. And so we could solve for this if we only could calculate the work done by that static friction force, which is keeping it from slipping. And in fact, we're going to show now that the friction force also does 0 work. Here is a blow up maybe of here's the inclined plane, and this is a blow up of the ball rolling down the plane. And remember that this thing is not slipping, so this point P, which at this instant where this photograph was taken, the point P is at rest. Now the friction force is pushing backwards like that, right? At this instant, that point just behind the point where it's contacting the plane is moving straight up, straight perpendicular to the plane, whereas B is moving straight down perpendicular to the plane. P is doing something that's right in between moving straight up and straight down. It's actually completely stationary with respect to the plane. So the friction force is being applied at point P, and it's pushing backwards, of course. That's what's causing it to roll without slipping. Otherwise, it would just slide down the plane. But notice the point at which the friction force is being applied to this ball is not moving. That's the important thing for whether a force does work. A force can only do work if the point at which it's applied moves through space in going from initial to final. And here, even though the point at which the friction force is being applied changes as it rolls down the plane, the point at which it is being applied at any instant is not moving. And so the friction force does no work as this thing rolls down the plane. Okay? So the static friction force is needed, otherwise it would slide down the plane, but it does no work because that point is not moving. And that means when we're applying W net by external equals delta KE plus delta PE, if we take our system to be just the gravitational force being internal, but friction and normal force is external, the net work done by external forces nicely is zero. And that means mechanical energy is conserved as this object rolls down the plane. So let's plug that in into our result in the problem we are working out here. The left-hand side becomes 0. All right, let's go to the next worksheet now. This is almost a version of what is asked for in the next worksheet. So you can refer back to that slide in setting up this problem. A solid ball of uniform density has mass 3 kilograms and radius 0.2 meters. Okay, so we're talking about a ball that's filled all the way through with a uniform density substance. It's released from rest at the top of a 4-meter long plane, inclined at 20 degrees to the horizontal, and we want to know the speed of the ball's center of mass after it travels the full distance down the plane, and it moves by rolling without slipping. So work on that. You can also answer part B once you've thought about that a little bit. We'll be back with the solution.